Good afternoon. This is Schweitzer, and little discussion here on gas collection. This is a pretty common topic when we're talking about states of matter. So it's a topic in the chapter of states of matter, potentially when we're talking about gases. It is a very common topic when involving stoichiometry. And again, with gases, PIV PV equals nRT is pretty common. It also very often is used to determine molar mass of a gas, otherwise known as molecular weight. Okay, so first things first, what does it mean for gas collection? Well, if we have a chemical reaction that is giving off a gas, let's say we take and you just use a crucible. I don't know, there's a lot of ways you could do this, but we have a gas of some sort. Baking soda would require some heat. Sodium hydrogen carbonate would break down with a little bit of heat or a catalyst of some sort. Sodium oxide plus water plus carbon dioxide. And at this point, this is a gas and this is a gas. How would we know how much gases are coming off of here? So in this case, we could trap them somehow, but we really wouldn't know unless we literally physically collected them. So a typical problem would be, okay, if we have, let's say, X amount of grams of this baking soda, how much water vapor would we get? How much carbon dioxide would we get? So again, this is just an example problem. The problem doesn't change, or doesn't matter. We're really referring to gas collection, and this is often referred to as the most common way is gas collection over water. So what we do is we have some way of using water displacement and the bubbles given off by the gas would therefore displace water, and then you would know the volume. So a pretty typical example would be to use a gas collection tube. Now there are two types of gas collection tubes. We have open gas collection tubes and we have closed gas collection tubes. I'm just going to draw out a typical example of an open, and I might show a more typical example we might do. If you were to take a glass tube, hook it to, the whole thing could be glass, doesn't matter, to a sealed vessel, and then this sealed vessel would then be used for a chemical reaction to take place. At some point, we have the atmospheric pressure pushing down on this thing, and because of the chemical reaction occurring, we have a pressure building up inside this thing. The overall goal typically is a PIV problem, PV equals nRT, and almost exclusively we're looking for N. So we would, again, there's different ways we could do this. I'm not saying I'm not able to do it with this one, but N could potentially equal PV over RT. Alright, so then either way, you would see this problem, and you would see the fact that the two arms are not necessarily equal. Okay, and so in the problem we described, that one arm is at one height and the other arm is at the other height, and you would simply have height 2, height 1. Subtracting these two heights would give you essentially the height of the difference in the water. So at this point, because the atmospheric pressure is pushing down, we would say the pressure of my gas is pushing the pressure of this height of water. If it happens to be water, let's just say in this case it's mercury. Mercury is a more common, at least on paper, because I'll talk about in a moment. But either way, mercury is right there, and then plus it's pushing down the pressure of the atmosphere. At that point, if you want to know the pressure of the gas, you could straight up plug in from something collected the pressure of the atmosphere. You'd have the pressure of the height. Now, if this is in mercury, then millimeters of Hg is one of our forms of pressure. And then you can just plug it in. But, and again, we're trying to find this guy. So if you had these two values, you just plug them, add them together, and you have this pressure. So quick little side note on why mercury is nice. Well, mercury is 13 times more dense than water, 13.3 to be exact. So that being said, equivalence height-wise is that the more dense you are, the less height you get. So this is a reciprocal relationship, and it looks simply like height 1, density 1 equals height 2, density 2. So if I have, and this is not a real common calculation on an AP exam, but essentially it's a 13 to 1 relationship between water and mercury. So if they're not using mercury, let's say they're using water, then you would need, before you can plug this in here, you need to find the equivalent height in mercury. Of course, if you had a column that was 13 inches high, well, that of H2O, that would be equivalent 1 inch for mercury. Just a quick methodology. But you'd plug in your height of your water. This would be given. This would be 1. Then we go 13, and then solve for the equivalent height. So, moving on. Next would be a closed version. Okay. In this case, closed version might look something like this. You have a closed meaning we're closed to the atmosphere, and therefore the atmosphere will not play a role. And again, this is just given in the problem. We'd have at some point a level of mercury, and it would give you again the heights, height 1, height 2. In this case, the pressure of the gas is equal to the change in the height. Again, the height could have an issue of mercury, which is usually what it'll give you on paper, because then you can use the units easily. All right. Now, in a more common example, lab-wise, gas collection over water is pretty common. So we might do this type of situation where we have let's say we have a tube. This is what we will do in lab. Okay. And I usually use a 5-gallon bucket with it moderately full of water. Then we take a gas collection tube, which is just a giant test tube, and I start out with it relatively upright, I guess. Fill it full of water, and it fills up nicely. Okay. And place the old finger over the top of this thing, and you invert it into the water. Now, this would be an example of an open manometer, because it is exposed to the atmosphere. The top might be closed, but it has atmospheric pressure here. Okay. Now, At this case, we then have some way of having a chemical reaction. And let's just draw this right here. And it will be a multitude of different ways. Chemical reaction taking place in a closed vacuum cell. And this thing simply has a tube. And the tube would then drive gases. And they would bubble up and they'd bubble into this test tube. The test tube would then start to look like this. Let's redraw my picture here. Alright, there's my water line. And I have my test tube. I'll draw a smaller version of this test tube. Alright, here's my water line, and I end up having some gases displacing some volume. So inside here, I have my gases. Alright, well at this point, the pressure of the gases inside here is equal to, well, on one side, well, let's see what we got here. Forces wise, I have the pressure of the atmosphere pushing down on here, and then I have the pressure of the gases is taking the path of least resistance this way, and of course I have this water height being placed above this particular thing, this height here, and gravity is pulling this guy down here, height of the water here. So the pressure of the atmosphere is on one side of the teeter-totter, and on the other side I have the pressure, the pressure of the gas plus the pressure due to the height of water. Now again, because we're using water, I could use my reciprocal relationship and convert this over to equivalent, height of Hg in millimeters, and then I could just use it as is. But what we generally do with this is, because we're using such a large bucket, we take and we shove the test tube into the water until the levels are equal. Okay? And at this point, all of these gases inside here will have a little bit less room to move around, but you will see the volumes will change from, I don't know why it does that, but the volumes will change as you shove it into the water. Either way, because the height is 0, this guy is now gone. Okay? And the pressure of the atmosphere equals the pressure of the gas. Okay? That is pretty common for any lab procedure we might do. For one more thing I'd mention here is, if we were to analyze this sort of picture of what's going on in here, we have this very large test tube here, and I have gases inside of here that I basically dropped in. Let's call them X. And they're flying around, creating collisions and pressure, and therefore they push water out. So very often, again, we're looking to find the pressure of this gas. I'm going to call it gas X, because then I can take in this case, the PV equals nRT, and I can say, okay, well, N is equal to RT over PV, and of course I would take my pressure and plug it in here. But there's one small thing here, and that because I'm collecting over water, water also vaporizes into the solution. Not a lot, but of course at certain temperatures it does it more than others, and as you warm it, the vapor pressure of water tends to increase as well. But usually typical room temperature, let's say 25 degrees Celsius, the vapor pressure is quite small. It might be somewhere along the lines of 23 or so. I didn't look that up, but it'd be something small along that lines, millimeters of Hg. That's the equivalent pressure of 23 millimeters of mercury. Okay, so that means that somewhere just in your couple, not a lot, maybe I draw 3 of them there, water molecules that are contributing to the pressure. So Dalton's law of partial pressures says the total pressure is equal to the sum of the pressures we have. So I have the pressure of my gas X equals plus the pressure of the H2O. So in this case, this actual pressure that we're thinking isn't actually all the stuff we put there. Some of that pressure is due to water vapor. So if this pressure was, let's say, 750 millimeters of Hg, actually let's do the total. Let's just say atmospheric pressure for that day was 750, okay, hypothetically. This is 750, and at 25 degrees Celsius, hypothetically, it's close, 23. I want to find the pressure of just my gas. I would subtract the 23 off, and at that point, and it would be 727 millimeters of Hg. Just simple subtraction there. Okay, so kind of a lengthy little discussion into gas collection, but pretty much here is going to cover a whole bunch of different situations.